Dear students, in the last class we are discussing on the constructional details of three-phase induction machine. We have two types of three-phase induction machine, that is squirrel cage type and slip ring type. The difference is on the rotor side. And today we will discuss on what is meant by rotating magnetic field and the principle of operation of induction motor, that is three-phase induction motor. Then the expression for the speed of operation of the motor and the frequency of the induced EMF on the rotor side. When we are discussing the construction of three-phase induction motor, we had already mentioned on the stator side we have a three-phase winding and we will be providing a three-phase balanced supply. Whenever a voltage of three-phase is applied to the stator side, there will be a current that is flowing through the winding, and corresponding to the winding current there will be a flux produced. And if you consider the whole system, the flux that is produced will be in phase with that of the current that is flowing through. And in the slide we have the phasor diagram that is given corresponding to the flux produced. Since it is a balanced current that is flowing through, we have a balanced flux of phi m that is produced. And when we consider each phase, the magnitude of flux that is produced is equal but displaced by 120 degree, and it rotates in anti-clockwise direction with an angular velocity of omega. And the equations for each phase are given as phi r equal to phi m sin omega t, phi y equal to phi m sin omega t minus 120, phi b equal to phi m sin omega t minus 240. The same is shown along with the stator winding. We can see the magnitude is the same for each phase and displaced by 120 degree. The flux waveform is shown. It is sinusoidal in nature because we have given a sinusoidal three-phase supply, and the current corresponding to the same will be sinusoidal, and the flux will be in phase with that of the sinusoidal current, and they are displaced by 120 degree from each other. Now we will analyze the flux of each phase considering a particular instant. Here in the slide we consider omega t equal to 0, and we have written the corresponding magnitude. On the left side we can see the general equations and the phasors, and at the time omega t equal to 0 we can find phi r, the magnitude is equal to 0, phi y is equal to minus 0.866 phi m, and phi b equal to 0.866 phi m. That is obtained by substituting omega t equal to 0 in the equations for phi r, phi y and phi b. The original equation, phi m sin omega t minus 120, phi m sin omega t minus 240. And the corresponding magnitudes are drawn on the phasors, and the resultant is found out, and we can see the resultant is having a magnitude 1.5 phi m and in vertical upward direction. With the color that is given to each phasors, we can understand the direction why it is selected so. For phi y, it is taken in opposite direction to the original phi y direction, That is because the magnitude that we obtained for 5i at omega t equal to 0 is minus 0.866 m. So we have drawn in the new phasor opposite the direction of 5i in the actual diagram because it is minus, and 5 for 5b it is taken in the same direction itself because the resultant that we obtain when omega t equal to 0, 5b is equal to 0.866 m. There is only the magnitude difference, no directional difference. For another instant, that is omega t equal to 30, we will be considering the three-phase system. Here we will get the magnitude for phi r, phi y and phi b as phi r equal to 0.5 m, phi y equal to minus 1 phi m, phi b equal to 0.5 m. And we can see the resultant will be having a magnitude of 1.5 m. We can note in the phasor diagram that is given. Phi r is equal to 0.5 m is drawn in the same direction as that of the original phi r itself, and phi b is drawn in the same direction as that of the original phi b with a magnitude of 0.5, and phi y is drawn in opposite direction to the original phi y because it is minus 1 phi m, and the resultant for phi b and phi r is obtained along the direction of phi y in the phasor, and we will get the total resultant magnitude as 1.5 phi m. Again we consider another instant, that is omega t equal to 60. We have the magnitude for phi r as 0.866 phi m, phi y as minus 0.866 phi m, and phi b is equal to 0, and the resultant is obtained and is having a magnitude of 1.5 phi m. And comparing with the previous case where omega t is equal to 30, for omega t equal to 60 degree, the resultant is again rotated by an angle 30 degree from the previous case in clockwise direction. And keep in mind, the resultant magnitude is same for all the cases. Here again we consider the phasors for omega t equal to 90. Omega r is equal to 1 phi m, phi y is equal to minus 0.5 phi m, phi b equal to minus 0.5 phi m. And we can find out the resultant for these three phasors as 1.5 phi m, and that is again rotated by an angle 30 degree compared with the previous case in clockwise direction. So now we will consider a diagram or phasor where we consider for omega t equal to 0 to omega t equal to 90. The resultant at each instant is having the same magnitude, that is 1.5 times that of phi m, but it is rotating from a particular position at omega t equal to 0 in clockwise direction, and we can see the angle of rotation is same as that of the instant that we have considered. If omega t is equal to 90 degree that we have taken, the resultant also have rotated with the same angle in clockwise direction. So the four instances that we had considered is shown in the figure. So we can see at each instant the resultant is rotating in clockwise direction and it is having a magnitude as constant as 1.5 phi m. So from the previous analysis we have found that the magnetic field that is produced will be rotating in nature if the supply is polyphase type. Now we will consider the working principle of a three-phase induction motor. So remember the constructional details of three-phase induction motor. On the stator side we have the three-phase winding and we will be providing a three-phase supply. On the rotor side we have either the slip ring arrangement along with the three-phase winding itself, or there will be copper or aluminum bars that are placed in the slots of rotor core and with end rings short circuiting all the conductors. So whenever a three-phase supply is provided to the stator winding, there will be a current that is flowing through, and corresponding to that there will be a magnetic field that is produced, and the nature of magnetic field produced will be a rotating type, and it will be rotating at a particular speed which is called as synchronous speed. The speed of rotation of the magnetic field will be Ns is equal to 120 F by P. The rotor is at standstill condition, and we have the Faraday's laws of electromagnetic induction. Whenever there is a rate of change of magnetic flux linkages with a circuit, there will be an induced EMF on the same. So on the rotor circuit we have a conducting material or winding, and the magnetic field that is produced on the stator side is rotating in nature. Because of that there will be a rate of change of magnetic flux linkages which are linked with the rotor circuit, and there will be an EMF induced on the rotor conductors. In the case of winding or the rotor bars, it will be short circuited through the end rings or through the resistances that are attached, and because of that there will be a current that is flowing through the winding. And we have the Lenz's law which gives the direction of induced EMF, where it says the direction of induced EMF is such that it will oppose the cause of production of it. Here we have the cause of production of induced EMF is the relative velocity between the rotating magnetic field and the rotor conductors. The rotating magnetic field is rotating with a speed of ns, that is synchronous speed, and rotor conductors are at standstill condition. So to oppose the very cause of production of induced EMF means to reduce the relative velocity between the rotating magnetic field and the rotor. For that, the rotor should be rotating in the same direction as that of the rotating magnetic field, by which the relative velocity between the rotor and the rotating magnetic field will get reduced. So that is the principle of operation of three-phase induction motor, and we can find that the rotor will start to rotate in the same direction as that of the rotating magnetic field. And one more thing that you will have to keep in mind is the rotor will never be attaining the same speed as that of the rotating magnetic field, because once the rotor attains the same speed of rotating magnetic field, there will never be any more induced EMF in rotor conductors, because the relative velocity is equal to 0, or the rate of change of magnetic flux linkages with the rotor conductors will be equal to 0, and no more it will be acting as a motor. As I had already mentioned, the speed of rotating magnetic field is called the synchronous speed, and it is given by the equation Ns is equal to 120 F by P, where F is the frequency of the supply and P is the number of poles of stator winding. The speed of the rotor will be always less than synchronous speed, and the speed of the rotor is given by n. We have a time slip which is given as ns minus n divided by ns, or the percentage of slip is given as ns minus n divided by ns into 100. So we have two conditions for slip S, that is when n is equal to 0, that is when rotor is at standstill condition, the starting condition of induction motor, S will be equal to 1, and if it attains a speed of ns, then slip will be equal to 0. In the case of induction motor, if the machine is run at no load condition, the speed difference will be only of 1%, and if it is fully loaded, the speed difference can be of 3 to 5%, and we can consider the induction motor to be of constant speed type. We will find the expression for the frequency of the rotor current. We have the equation ns is equal to 120 f by p, and the equation can be rewritten for the frequency of the supply. F is equal to p ns divided by 120. And we know the frequency of the current induced on rotor conductors depends on the relative velocity or relative speed between the rotating magnetic field and the rotor, that is ns minus n. We have from the equation for slip S is equal to ns minus n divided by ns. We can write ns minus n is equal to sns. So the equation for a rotor frequency can be written Fr is equal to P into ns minus n divided by 120. And rewriting the same, we can find Fr is equal to Sf. That is, the rotor frequency will be equal to slip into the frequency of the stator. So when we consider the two extreme conditions, when S is equal to 1, the rotor frequency will be equal to the supply frequency or the stator frequency, and when S is equal to 0, or when the rotor runs at speed ns, the frequency of the rotor current will be equal to 0. Fr is equal to 0. So the frequency of the rotor current can vary from F to 0. So hope you have understood the principle of operation of induction motor. Then what is meant by rotating magnetic field and the frequency of rotor current. Thank you.